Hello, everyone. Welcome to our live session today. We are excited to see everyone, or at least hear from you in the chat. My name is Matthew. I'm one of the instructors for our online courses and our education programs. Vicki is helping us out behind the scenes. Thank you, Vicki. And Chris, I'll let you say hello to everyone, and then we will get started with your questions. Please post those in the chat, and we'll grab them from there.
Okay, welcome everyone to another online live session for people taking the MOOC or people who just encounter this by some other means. So happy to take your questions on any subject in astronomy.
All right, the very first question we have is from an email. Steve Callender asks, the field guide research study led by UA's Megan Mansfield suggests, I think, that water molecules exist in hot Jupiter's atmospheres, but given the extreme temperatures, how is that possible?
Well, on some of the exoplanets that have very high temperatures, they basically have atmospheres containing steam. So that's the form of it's a vaporous form of water at very high temperature, and that's not unusual. Steam has now been detected, I think, by spectroscopic means in the atmospheres of probably 6 or 7 exoplanets, mostly hot Jupiters, but I think one super Earth. So again, these are all pretty hot planets on nearby orbits, so they're technically hot Jupiters.
And then a follow-up to that, since hot Jupiters are tidally locked, creating a huge temperature difference between their hot and cold side, does convection cause their atmospheres to be distorted to the cold side, and does that distortion affect their orbits?
Well, it's a subject to interesting modeling, what happens to a tidally locked hot Jupiter. I mean, there are a lot of these type of exoplanets, so it's a pretty important category. And so there is reasonable modeling, three-dimensional atmospheric modeling of what might happen. And when there are convection currents or convection cells within a deep atmosphere of a gas giant, that does facilitate thermal conductivity or heat transfer. And so the heat does transfer around the planet, but it doesn't reach an equilibrium temperature. In other words, there is still a cold side of the gas giant and a hot side of the gas giant. The degree of that diffusion really depends on the depth of the atmosphere and the pressures throughout the profile of the atmosphere, and we don't have that information yet on any hot Jupiter.
So there was some exciting astronomy news since our last session. There was a Sagittarius Astar image that came out. Astrocellist would like to know if you could just talk about your thoughts on that image and maybe talk about what it was, what it is, and what you think about it.
Sure, I'll give the high-level summary, and then if people have follow-up questions, I'm happy to go into more detail, because it's a pretty big announcement. So this is the Event Horizon Telescope Consortium, which includes a number of scientists at the University of Arizona, many of my colleagues, faculty, postdocs, and grad students. It also involves, in the interferometer array of telescopes, it involves a telescope on Kitt Peak nearby, as well as telescopes scattered as far away as the South Pole. This is the second image ever made of a black hole, or rather the shadow of a black hole and the hot gas surrounding it. And Sagittarius A** is the name given to the extremely compact radio source at the epicenter, the exact dynamical and gravitational center of our galaxy, the Milky Way. So this is 27,000 light years away, more or less. And this black hole, coincidentally, was about equally easy to observe, or difficult, depending on your point of view, to the first discovery that was announced a year or so ago of M87. So compared to the black hole in M87, the black hole in the center of our galaxy is 2,000 times less massive and 2,000 times smaller. But it's also a lot closer, and that meant it was just about the same angular resolution type of observation, which meant it was, on the same field, on the same landscape in terms of observational difficulty. The complicating factor, however, is that the black hole material rotates near the event horizon very fast, whereas M87 black hole near the event horizon material orbits in days or weeks. In the galactic center black hole, material literally orbits in minutes or hours. And so because of the flickering brightness of this material close to the black hole, they had a very difficult data analysis job to combine all the images when the actual brightness of what they were observing was changing, was flickering on that time scale.
That's interesting. Can you talk a little bit about how they deal with that flickering? I mean, I guess why is the time resolution such a challenge for this, and what are the possible solutions?
So the issue with these observations is that there's two fundamental determinants of the quality of the data. One, of course, is the angular resolution. So without the angular resolution, you would not be able to resolve the event horizon and that disk of material, that dark hole surrounded by bright material. So you need the angular resolution, and that comes from the wavelength of observation and the largest separation of the telescopes in the array, which is roughly Earth diameter. And the second is sensitivity. So these are difficult observations because the objects under discussion are pretty far away, and their level of emission in millimeter waves is quite modest. And so the problem is when you're limited by sensitivity, you have to gather a lot of data to be able to get above the radio noise or the ambient noise. And in the case of M87, they could just stare at the object for days, basically, and put all that data together into one image. For the galactic center black hole, the flickering of the actual brightness of the torus of hot gas around the black hole on timescales of minutes or hours meant they had to do a very complicated image analysis to be able to combine it to detect it in the first place and end up with one map. And basically, they used supercomputers. And as far as I recall, they made millions of simulations of models of how that flickering and varying brightness occurred on the timescale of their observations to be able to understand it well enough to combine all the data. So that took weeks and weeks of supercomputer time, and that's part of the reason why this didn't get published before it did.
Excellent, thank you very much. If other people have questions, follow-ups, you can post those in the chat. But we will move on to the next question. Sharon is in India and is moving into grade 12. Can you talk a little bit about career paths to becoming an astrophysicist or an astronomer?
Typically, the career path in school it's not that critical, and it's pretty unusual around the world to have astronomy classes taught in high school. You just have to be lucky that it's either allowed in the curriculum or that a teacher is knowledgeable and interested enough to offer an astronomy elective or special class. So it's pretty unusual to have any astronomy before you get to college. At college, the base coat of paint, if you like, to be an astronomer or an astrophysicist is physics, because astrophysics is essentially the projection of the laws of physics and the study of physical phenomena into the universe. And so physics is the dominant study subject for undergraduate work as a prelude to doing astronomy. Now, some programs in the United States and fewer elsewhere have physics and astronomy programs where you can major in astronomy solely or in a combination of astronomy and physics. For example, our astronomy majors here at the University of Arizona, that they have 70% overlap with a physics major. So they're taking a lot of math and physics anyway. But physics as a background is fine. And then at graduate level, you would move into more particular astronomy courses. In a master's program or a PhD, you'd have a set of courses that will be pretty much purely astrophysics. And that's where you get the detailed information about astronomy and how the world of science and how physical law applies in the universe.
SST11, who's on with us live, asks, why is the speed of light the ultimate speed limit?
Well, it turns out that it's a fundamental law of physics. The fact that the speed of light is constant regardless of the motion of the observer was an experimental result of the late 20th century, the Michelson-Morley experiment. I think it was 1894. Michelson-Morley experiment was a null result where they used an optical interferometer to show that the measured speed of light did not depend on the Earth's motion, on which side of the sun it was or which time of year, and therefore the speed of light was impervious or oblivious to the fact that the Earth was moving around the sun. And generalizing this, they reached a conclusion there was no ether, no invisible substance with respect to which the speed of light was 300,000 kilometers per second. It's a universal number regardless of the sense of motion. And therefore, the premises of special relativity emerge as articulated by Albert Einstein. The fact that it's an absolute limit is also connected with other physics, E equals mc squared, for example. In special relativity, as you make an object try to move nearer and nearer the speed of light, the energy you put into its increased motion or speed ends up going into its mass by E equals mc squared. So you make the object's inertial mass heavier, and it never reaches the speed of light because of that. Essentially, you'd have to put an infinite amount of energy in, and you'd asymptotically approach the speed of light, but never reach it and not exceed it. So the constancy of the speed of light, regardless of motion, and its status as an absolute speed limit in physics is cemented by the theory of relativity.
The next question is from Martin Gillum, who sent an email, who would like to know if we have now completed the theoretical periodic table of elements. We seem to have discovered enough elements to completely fill the outermost shell of electrons. Is there a chance that we could ever transcend into elements with the next layer of electrons?
Well, the periodic table has been known and complete at the level of stable nuclides, out to uranium for decades. What's new and what still is a subject of lab and physics research is the transuranic elements, that is the extremely high atomic numbers that are intrinsically unstable. So these are chemical elements. They do extend the periodic table, but they're fleeting because they're not stable. Their combination of neutrons and protons renders them radioactive and decay on a very short time scale. I think fleetingly, elements up to the atomic number of 122, maybe 126, I'm not sure, the record breaker at the moment, have been created, but they're all very unstable with short decay times.
Excellent. And is it just that they require a lot of energy to create these higher order elements? I mean, is that something that we can create, or is it just a fundamental instability that we will never surmount?
We can create them. Basically, the method is to inject by collisions and particle accelerators neutrons into an already heavy atomic nucleus. As you move up the periodic table, the imbalance or the ratio between neutrons and protons increases slowly, and so the heavier elements involve injecting more and more neutrons into the nucleus, and that in turn renders it unstable. So it is possible to create them, but their instability is fundamental part of nuclear physics.
Excellent. The next question is sort of related, and we'd like your opinion on how reasonable do you think the science fiction trope is of finding magical new elements or minerals or alloys on planets outside of Earth? It seems like every science fiction show has a time when they find some, element or mineral with properties that are, amazing and miraculous. What do you think the chances are of us finding something outside of Earth, or do you think most minerals exist on Earth?
I think the odds of finding a new stable element that we don't already know as part of the periodic table are very small indeed, because all of those elements have been known now for quite a while, some of them obviously for centuries, and all of them have been discovered in space. Interestingly, as a historical note, the first element that was found in space and not on the Earth was helium. It was observed in spectroscopy of stars, and astronomers called it nebulium because they really thought it was a new element that might exist in space and not on Earth. But eventually, of course, we recognize helium does exist on the Earth. It's quite a rare element on Earth, but it can be found and liberated, and underground it often seeps out at a measurable level. So there's been no exception to this rule. Basically, the elements we see on the Earth are the same as the elements we see out in space. We've not found elements on Earth that we haven't seen in space, and vice versa. We've not found elements with spectroscopy in space that are not apparent or creatable on Earth or discoverable on Earth.
There's been some interesting news about entangled particles. That's about possible future of the internet. Lawrence has a question about entangled particles. If I have two entangled particles that are widely separated and particle one falls into a black hole or encounters an antiparticle, then what happens to the second particle in those situations?
Right. So this is a theoretical consideration that is non-trivial. I mean, it's of great interest, actually. What is the situation if you have quantum entanglement at the event horizon of a black hole? The quantum physics would say that the entanglement should continue, but clearly information is lost beyond the event horizon. So the relativity, the general relativity, would say that the entanglement could not survive the one particle falling into the black hole. Now, physicists have gone to reconcile this inconsistency. They've invented ideas such as a firewall, that this is a sort of intense radiation field around a black hole outside the event horizon that essentially destroys the correlations between quantum particles or the entanglements of an entangled pair. The truth is, it's an experimental question, and so you'd actually want to do the experiment. But the relativity at the moment seems to be in charge. In other words, if you could have an entangled pair where one particle was out and one was in the event horizon, then you can interrogate the system and therefore learn something about within the black hole, which is against general relativity.
The next question is from Michelle Fantvey, who is on with us live. I'm wondering how we know the age of the universe if only a portion of it is visible to us.
Well, it's an indirect experiment. So the age of the universe is an observational number, but it's derived in an interesting way. In one way, it's derived from the expansion model. So it's true that there are parts of the physical universe we can't see because they were moving away from us faster than light. They're outside our horizon. It's a technical description of that. However, we can measure the expansion rate locally. That's the current expansion rate. And we can look out in space and measure the expansion rate back in time. And we can do this pretty reliably now over 3/4 or 80% of the age of the universe. So with that span of data and that time of tracing the expansion history, it's fairly reliable to infer the full age of the universe because you're seeing most of the way back through the expansion history anyway. So that's one method. The independent method, of course, is to look for the oldest objects you can find in the universe, where you measure their age by some other astrophysical technique, such as the age of a star, based on models of stars. So that's independent of the Big Bang or any inference about the expansion history. And the age of the oldest stars is consistent with the 13.8 billion years you get from an expanding universe model. So these things essentially cross-check.
The next question is from Little Empty Attic. Have we gotten any answers as to why the orbits of our planets seem different from those of other systems?
No, it's an interesting question. As in May, if you keep track of this on the NASA exoplanet website, the number of confirmed exoplanets passed 5,000, an amazing number. And the number of candidates is another 9,000. So we're up to 4, and most of those candidates actually are about 90% likely to be confirmed if we had the resources to do so. So if you put that 90% of the 9,000 and the 5,000 together, we're talking about, well over 10,000 exoplanets, which is pretty impressive. And we have many systems. There are something like 1,800 systems, planetary systems, where there's more than one planet found in the system, ranging all the way up to 8 or 9, as rich as our solar system. And it is true that we haven't found any clone of our solar system yet. We found clones of the Earth pretty much, but not systems that are like ours. The two most common categories of exoplanets are mini Neptunes and super Earths. And in our solar system, there are no mini Neptunes and no super Earths. So it's a good question because our solar system is looking a little anomalous at this point. That's not to say that we won't find a system that's roughly like ours. But a system like ours appears to be in a small statistical minority in all the planetary systems we found so far.
The next question is from Jan Campos, who sent an email regarding the Sagittarius A-star image. Can you talk about the tilt of Sagittarius A-star to the plane of the galaxy, and does that, or how does that affect our ability to image it?
It does have some effect. The tilt is not an actually very well measured number, and it has, of course, to be modeled in the data. You also have to remember that there's pretty extreme distortion of light happening in that image. People were talking colloquially and in the press about, even the scientists who discovered it were talking about the shadow cast by the black hole. But technically it's not a shadow, because the shadow in optics is something blocking light and then the straight lines of the light delineating an object behind which is darkness. That's not this situation. The relativity is so intense near the event horizon that light is being bent around the black hole. So when you see the light in that image, you're actually looking behind the black hole. And that modeling of the gravitational lensing, because that's what the effect is, actually complicates getting something simple like an inclination angle. So I would say the inclination angle is not that well measured, and it's not measured by any other method either. We know what the geometry of the center of our galaxy is, and we could argue from angular momentum terms that the central object should have a certain angular momentum vector, and that's pretty much where the inclination angle comes from most reliably.
Pari PM would like to know if you have any books that you can recommend about astrobiology.
Well, there's a lot of astrobiology going on, and there's a lot of books. In terms of the hunt for exoplanets, I'm going to recommend my own book, which will come out in the spring. If you can wait till the spring, I have a book called Worlds Without End that will be published by MIT Press. If you're really impatient, though, Elizabeth Tasker had a nice book a couple of years ago called The Planet Factory. I recommend that one highly. It's very well written. So that's about exoplanets. On astrobiology more generally, there's a variety of books. It's a fast-moving subject, and actually I think it's almost better to find articles, individual articles, because things are changing so quickly. It's also a very big subject, which includes everything from the history of life on Earth to the search for life in the solar system to exoplanets to SETI, and it's pretty hard to put all that in one book. So for some astrobiology, if you really want to get the current view, you're probably better looking at articles than a book right now.
Isla137 asks, does observing an event change its entropy?
Well, in physics, in the quantum theory, we have the premise that the act of observation alters the state of a system. That is a profound and fundamental aspect of quantum physics, because when you interact with a system to measure it, you have to interact with it in some way, by shining light on it, by using a probe, by measuring its magnetic field. Whatever your detection system is, it affects the system in state. Now, those impacts of observation don't necessarily and usually affect the entropy, but they certainly affect the position and the momentum if it's a particle. That leads to the Heisenberg uncertainty principle. And they also affect the energy, which is another representation of the Heisenberg uncertainty principle. So in that energy is a related quantity to entropy, yes, the entropy of a system can be affected by observation.
The next question is from H.J. Bell, MD. What is the difference between cosmic inflation and the concept of eternal inflation, or are they parts of the same theoretical framework?
They are part of the same overall framework. The basic idea of cosmic inflation is the idea, generated by, most notably by Alan Guth in 1980, that there was an initial, very early, first fraction of a second after the Big Bang, exponential expansion of the universe by 30 or 40 e-foldings to take it from a subatomic size state up to a macroscopic state, after which steady and slower Hubble expansion continued, generated by some quantum field that's nature we don't understand. And in that formulation of inflation, it's a singular event. It's just a very early description of the Big Bang. In the eternal inflation model, people reached behind inflation itself to wonder what kind of field could create the inflation event. And in the understanding of the field that could do that, they realized that fluctuations, quantum fluctuations in that field might easily generate other events, other space-time expansions, other space-times. And that, of course, doesn't have a time frame attached to it in the theory. And so it can be eternal. And so that's eternal inflation. And that's a prelude to the idea of the multiverse.
The next question is from Nikki291278. I have read about the stellar fossil magnetic fields, but I could not find much information about them. Could you explain what exactly they are and why are they important?
I'm not totally sure of the reference for the question, but magnetic fields, stars have magnetic fields, and the magnetic fields are entrained by the plasma because you have a gas where the charged particles are separated. There are no stable atoms, and that allows the magnetic field to be entrained. And you can, of course, have a dynamo mechanism which will create and destroy that magnetic field. So, in a sense, that they're fossils, they represent some initial state of the star because the magnetic fields were not created after the star was formed, but they must have at some level been a primordial field that was there as the star formed. So they're telling us something about the formation process of the star.
So another possibility could be that she's asking about how magnetic fields are from the sun, from the Earth, I guess, could be frozen in rocks on the Earth. So maybe we can talk about that process too. And if that's not what she's talking about, then maybe we'll have covered both of them.
Right. So magnetic field on the Earth, the magnetic field is obviously essentially a dipole field, and it's part of it's generated. And the fact that it's so strong is generated because we have a liquid core. We have a solid and metal, iron and nickel core, and then also a liquid part of the core. And this is also where the dynamo mechanism can create and then destroy the magnetic field. And the wrapping up of the magnetic field and its winding and then tangling and then destruction periodically is what creates the 22-year, or rather the much longer timescale reversal of the Earth's magnetic field. And then to measure that reversal and history of the magnetic field, we can look at rocks. We can look at magnetized minerals in rocks. Magnetite actually is a mineral that was known to the ancient people. I think ancient Babylonians, Egyptians, civilizations around the Mediterranean thousands of years ago were able to use magnetite to make primitive forms of compasses to navigate. So the magnetized mineral of magnetite has been known for thousands of years. And in the modern age, geophysicists just find these particular grains that can entrain and fossilize, if you like, a magnetic field to talk and try and find rocks that have been unaltered for long periods of time. That's important. And then they can reconstruct the history of the Earth's magnetic field. And this has been done with some reliability.
The next question is from Hernan Reyes, who's interested in, sort of a hypothetical situation, what your thoughts are. Even if we could harness biology to put astronauts into some kind of suspended animation, would it make sense to send humans so far away to, on like a 10 or 15 or 20-year trip to Europa or the moons of the outer planets and have them wake up? Would it be even worth traveling out there, given all of the other hazards once they arrive, for that situation to be valid?
So there's a couple of parts to the question. I mean, one is just what is the plausibility that suspended animation in any form is a viable technology to apply to humans? And I think the jury is out on that. As part of the medical profession of, resuscitating people, who've fallen under ice and so on, there have been situations where people have been naturally put in a nearly suspended state. And then in more laboratory-like experiments, scientists have replaced the body fluids of pigs and dogs and other mammals that are models for humans, roughly, with some glycol-type hybrid medium that they will maintain their cell function. And these animals, it's an animal experiment, whether people like it or not, are revived with some probability of success after days and I think weeks. A few weeks is the longest. Well, that's a long way from putting humans on ice or suspending their animation for decades or centuries. So I think we're, decades away from even a viable demonstration of that kind of technology. And as far as the application to the solar system, I just don't think it's the right technology. The technology is probably essential if you want to go to the stars, because you're talking about millennium type trips there, and we just won't do it with humans unless somehow we can be put on ice. For the solar system, where the travel times may be a decade or two, I think the way it might happen is by brave, adventurous people who essentially devote their life to this single voyage. They may be trained for it and travel out there as young people. They spend time getting there, spend time there, come back as middle-aged or older people, and that's what they did with their life. And that's an enormous sacrifice and a great, dangerous adventure, but what a singular experience. So I think it'll be done in an almost conventional way.
Excellent, thanks. And that was really addressing his sort of follow-up question too. So the next question is from one of our live participants. Einstein, in his special theory of relativity, talked about moving clocks running slow, or time dilation. So does this happen in real life situations, like clocks and rockets run more slowly than the ones we have on Earth?
Oh, absolutely. So this has been amply demonstrated. I think the first demonstration of it didn't use the clocks necessarily. You need, obviously, we can't make physical objects like a clock travel at any fraction of the speed of light. So you're left looking for very subtle effects of relativity at much smaller fractions of the speed of light, which means you need an extremely precise clock to do it. So in fact, it has been done. So we've been able to make atomic clocks or very accurate clocks move at sufficient speeds, thousands of miles per hour, and see the very small dilation of the time relative to a stationary identical clock on the ground. But the first demonstration that this effect was true was in a more dramatic way, because it was really relativistic, happened in, I think, the 30s and 40s, because some cosmic ray particles are charged particles that are unstable, that are radioactively decay. So there are nuclides involved in cosmic rays that have decay times, and you can measure the decay time in the lab easily. And these nuclides, some of them, were reaching the ground when they shouldn't have, because they were being created in the upper atmosphere, say, by spallation or some other process. And based on their calculated lifetime without special relativity, they shouldn't have decayed before they reached the ground, and we wouldn't have been able to measure them. But because they were traveling at relativistic, close to light speed, in their frame, the time was slowing down, which allowed them to reach the Earth's surface. So basically, the arrival of cosmic rays decades ago was a demonstration that time dilation exists, and we can measure it.
The next question is from one of our participants, H.J. Bell, MD. What genetic modifications might be helpful when thinking of humans colonizing Mars? I mean, anything from something simple to something like introducing chloroplasts into human cells for low oxygen, high CO2 environments.
Right. So there are some quite specific genetic modifications that have been proposed or considered. I don't remember the names of the actual genes involved, but the obvious ones are, they're genetic adaptations that will allow people to deal with reduced gravity, for example, because the vascular function and the capillary action is changed in the body in a Martian environment. There's also the question of keeping strength in the bones, because the resistance is lower when you're in a weakened gravity. It's only 40% of the Earth, but that's a fraction that would affect strength of bones and lead to osteoporosis. So there is a genetic modification that might help there. The extreme option that you're talking about, chloroplast, is a fascinating one because it's basically suggesting that humans might be most efficient if they use the mechanism that plants use to get their energy, photosynthesis. In other words, rather than eating food and metabolizing it, a rather inefficient process, just harvest energy from the air. And I think the people who've thought of this have actually done the math, and it's possible, but only if a future human had this particular chloroplast modification. They would have to have a skin area about the size of a tennis court to gather enough energy to live. And at that point, you've distorted a human so grotesquely, I think, and dramatically that it's hard to call them a human anymore.
The next question is from Sana Kashmiri, who asks, why do we always see the same side of the moon?
Well, because the moon is tidally locked to the Earth. The moon is by far the largest satellite, natural satellite of a planet in the solar system compared to the planet's size. There's no similar, even though there are some large moons of Jupiter and Saturn. Those are gas giants, so they're vastly larger than their moons. Mars has 2 tiny moons, Venus has no moon, Mercury has no moon. So our moon is very large satellite, quite close to the Earth, and the tidal interaction between the two naturally leads to tidal locking, because as this, gravity is reaching out and grabbing the moon, and it tends to grab it in a sense that it slows its rotation and eventually has the same face facing the Earth. And that's been the case for billions of years.
David McKenzie sent an email. How do professional astronomers such as yourself keep from being overwhelmed by the sheer size of the universe, along with all the discoveries made so far? It seems like it will be an impossible task to find answers to all the questions that are out there to date.
Mostly we use drugs. I'm just kidding. It is indeed difficult to truly contemplate the universe. I think the practical aspect is that astronomers do their work and their calculations, and they have dwelled with the aspects of the universe that we've measured for so long that they don't always consider it in those terms. They work the math and they talk about the physical properties and they solve a scientific problem, and they don't often drop back to the sheer vastness of the universe or the implications of, billions of habitable worlds in the Milky Way and so on. So it's a good point. Astronomers and scientists need to sometimes, set aside the technical work they do and the calculations and the science itself, and appropriately dwell in the vastness of the universe and the amazing attributes that we've measured so far. And it's easier for members of the public to do that because they're not doing the technical work alongside.
The next question is from Zegzi Warlock, who asks, do you think space junk will be managed in this decade and not cause significant effects on space travel?
I'd like to say yes, but I think, unfortunately, the answer is no. So the only good thing that's happened in the last few years is that no one is in denial anymore about the fact that space junk is a problem. It's a classic of what social scientists call tragedy of the commons. That's where a number of parties or interests benefit from something, but no one has the incentive to take care of it. And the result is that it can get ruined for everyone. So this isn't a phenomenon that you have other examples of in history. In this case, it's the space environment. Nobody's paid to take care of it. The incentive for taking care of it is only that if nobody takes care of it, then no one will get to use it at all. So people are no longer in denial, but the remedies are tricky because there's already so much space junk that all the various mechanisms people have thought, magnetic collections or harpoons to tether things, or scoops, or there are various, or just gravitational tethering of it and so on. There are all sorts of mechanisms, but they're pretty inefficient, and space is big. Even low Earth orbit is an enormous volume or surface area, if you like. So nobody has a remedy that's really going to turn the situation around. The best we could maybe hope for is not to make it get much worse. And that's mitigated against by the enormous ambitions of companies putting up fleets of constellations of satellites. we're heading towards, I think the number by the end of the decade will be about 50,000 small satellites in low Earth orbit, which is a fantastic number compared to the current number, which is probably 6,000 or 7,000.
The next question is from an email. Derry Bell Fernandez asks, when an exoplanet is found, how can we know what type of exoplanet it is? What instruments are used?
So exoplanet detection has two fundamental methods. The first used and producing the first 100 or so exoplanets is the Doppler method, and that uses the wobble, the gravitational wobble on the star induced by a planet to measure its mass and its orbital period. So that led to the first exoplanet discovery, the Nobel Prize that was awarded a few years ago, and has produced hundreds of the known exoplanets. The second method, which ended up being more successful, is the transit method, which is the eclipsing or transiting of a star by the planet and the dimming of its light temporarily. And the Kepler satellite found almost 2,000 exoplanets, just that one mission by that method. So those are the two primary methods. If you only had Doppler, you would only measure mass and orbit and distance of the planet. If you only had transits, you'd just measure the size and the orbital period and distance. If you combine the two, which has been done for a couple hundred exoplanets, you get both mass and size, and that lets you get density or average density. So that's an important step up. And it's that subset that have both techniques applied that really lets you distinguish between a super Earth and a mini Neptune and a gas giant.
Loki, who sent an appropriately chaotic question, is there any connection between the mysterious monoliths which have appeared on the Earth in several places and aliens? What is your view about their appearances?
I don't know the full story on monoliths. I mean, they come and go in the media occasionally, but I have seen follow-up to some monolith reports that have eventually identified the origin as, I won't even call them pranksters. I mean, sometimes they're, they're mystical. There's a mystical connection here, a sort of quasi-religious ceremony that's being planned. So everything I know suggests that the monoliths that are reported in the media are human creations used for various purposes. They can be mysterious because the people putting them there are either doing it literally to confuse people or to spoof them or prank them, or because they are doing something private that they don't want to talk about. So I don't see any evidence in those reports of alien artifacts. In particular, if there were alien artifacts, they're sitting there on the Earth, and we could take them or pieces of them into the lab, and scientists could show whether they involve technologies or materials that we can't create on the Earth, and that hasn't happened.
The next question is from one of our live participants. I believe the question has to do with the cosmic horizon, but they want to know, do we have any idea what or how much is beyond the cosmic horizon?
It's a good question, and no, not really, because the Big Bang model is such that we have a bound to the universe in time, but not in space. So the limit of our vision is defined by the age of the universe, essentially, and how far we can see out where light has had time to reach us in 13.8 billion years. And that's the limit. Now, the Big Bang model also has faster than light expansion for the early part of the history. And so we know there are regions of space-time that we haven't seen yet and can't see with our telescopes. But the Big Bang model doesn't say how extensive those might be. So the Big Bang model itself does not say what the size of those unobserved and possibly unobservable regions are. In other words, how much bigger is the physical universe than the observable universe? We don't actually know.
The next question is from Blick Ending, who asks, the man-made objects that are furthest away from the Earth are the Voyager and Pioneer probes. Can you tell us something about how far away they are, and what will eventually happen to them? Will they be destroyed?
And to those 4 probes launched in the 1970s, we had the New Horizons probe, I think launched in the 90s, which was the one that observed Pluto and is now headed out into the Kuiper Belt. So there are 5 man-made objects, spacecraft that are now have left the solar system. And their range of distances ranges, I think the full span ranges from about 80 astronomical units, which is twice the distance to Uranus and Neptune, and to 138 or 140. I think maybe the record is now 150 astronomical units. So that's how far these objects have gone. Now that's large, but it's not really leaving the solar system. Remember, the Kuiper belt extends out that far anyway, and then there's a comet cloud that goes out to 50 or 100,000 astronomical units, and the nearest stars are millions of astronomical units away. So if you do the math, none of these probes heading into interstellar space are going to be in the vicinity of any nearby star for tens of thousands of years.
The next question is an email from Cesar Angulo, who asks, I thought the perpetual motion was not real, but after reading an article, I'm confused. So now it seems like we can have perpetual motion only in atoms. Can you talk about whether this is a possibility on large or small scales?
Well, perpetual motion is a tricky concept because if you're talking about a physical object, a physical macroscopic object, then perpetual motion cannot exist, because if you can take some superfluid medium or superconducting magnet and you spin it, there's always some interaction, there's always some energy coupling, and that energy coupling means that the angular momentum will be transferred, and so the spin will stop eventually. Even take an object like a pulsar, which is an extremely compact magnetic star. That object, even isolated in space, will not spin forever because it's releasing gravitational radiation, and so that loss of energy and angular momentum will slow it down over time. So in astrophysical object terms, there's no perpetually moving object or perpetual motion. And obviously on the Earth terrestrial situation, you can't make perpetual motion happen because of conservation of energy. As far as atoms goes, it's a little tricky because formally we don't really consider an individual atom or a proton or a neutron to be in motion. We consider it to have energy states, and those energy states are described by quantum mechanics in a wave function. And that's not really motion in the normal sense we think of as motion. It's just a particular quantum described energy state.
All right, the next question is from, actually it's from last session, we just didn't get to it, but it was an interesting question, so I kept it. So Hernan asks, why is it that the Antikythera mechanism is so seldom mentioned when it must have been a fabulous aid to astronomical observations or thought and making use of such knowledge? Why do you think it is unsung, if not unknown?
So the Antikythera mechanism is, just to get the frame for the question, is a device that was an extraordinary device that was discovered over a century ago in the depths of the Mediterranean, a shipwreck. And it was a pitted, corroded, rusted, metallic object, impacted into the dirt and cemented into the dirt at the bottom of the Mediterranean. And it was rescued, and it wasn't really until the 1980s and 90s that research teams were able to use, MRI techniques and imaging to work through the layers and reconstruct what the original object was. So it's a long research project that eventually showed that it was an analog astronomical clock and timekeeping piece that also mapped out the motions of the planets, including their non-circular motions. This is all 2 millennia before Kepler. So it's a pretty striking piece. It's possible that this was based on a design of Archimedes, although there's not that much evidence for that. It's not clear if it was a unique object or not. It's always hard to find something this extraordinary and say it's the only one. It's just one that we found. It's probably was carried around the Mediterranean by the people who built it to show off. I mean, to trade with and to show other cultures wherever they were traveling in their boat that they had impressive knowledge and technology. Indeed, it is an extraordinary object, and I think the reason, to answer the question, the reason why it's maybe not more celebrated is that we have very little context for it. We don't know who built it. We don't know that it was based on an earlier idea of Archimedes, so we don't know who the inception of the idea came from. We don't know if it was unique. We don't know how it was used in practice. And so there's just too much we don't know about it. We have it as an artifact, a singular artifact of this time of 2 millennia ago, but that's almost all we have.
The next question is from one of our live participants, Heisenberg 3435. They just bought a telescope. Then they would like to know if you have any recommendations for books for amateur astronomers that might get them started.
Yeah, there are so many books actually. This is going to be hard because I'm not fully up on what's been published in the last few years. There's a classic book that goes back decades, but it's updated continuously, called Burnham's Sky Atlas, and that's a pretty good manual of the things you can see with a small telescope or binoculars or the naked eye. There's, to give a plug to someone I've known for a long time, Guy Consolmagno, who's now the director of the Vatican Observatory. He and a colleague wrote a book called Turn Left at Orion, nice catchy title, and it's about amateur astronomy and observing, and it's full of the pleasure of that activity, so that's one I recommend. But really there are an awful lot. And of course, Sky and Telescope, the magazine, monthly magazine, has columns, for timely and topical events that you can catch with your telescope. That's a periodical you probably want to subscribe to or look at.
The next question is from H.J. Bell, MD. Do you have any plans to continue teaching cosmology to Buddhist monks in the future? And what are the travel plans? Are there still travel restrictions? What are the things holding up programs like that?
Yeah, it's a good question. I would like to go back. It's been 3 years now. I did manage to go out there a year before COVID hit. COVID has essentially killed these programs pretty much. The Science for Monks program that I do and the Emory-Tibet Partnership program out of Emory University, they've been working virtually now for a couple of years, and I think they're just gradually coming back face to face. So I think and hope next year I might be able to go back out there. Also, they are trying to train local teachers. So the sustainable model for these programs is to have graduates from the first wave of programs know enough about science to teach other monks and nuns. And then you can propagate it without the moderate expense of taking Western teachers out and sending them to India or other parts. None of us get paid for our time when we teach in these programs, but they do pay our travel and they provide local expenses, which are not that expensive in India. As you probably know, India was extremely badly hit by COVID. They survived the first wave, got a little complacent, and all the best estimates based on excess deaths rather than the badly reported Indian government statistics suggest 8 times as many people died in India as the official government numbers, and that makes by far the largest death numbers and almost rate to be in India. So they've taken a while to recover from this devastating pandemic.
Excellent. Well, it is 10:55, and we are going to wrap up. Vicky and Michael are going to continue shortly with astronomy news. So stick around. But Chris, I'll let you say goodbye, say farewell to everyone, and we will be back. It's going to be 4 weeks before we are back again because a lot of the people on our team have travel. So the next time we'll be back is June 22nd, I believe. It's in our emails, but go ahead, Chris.
Right. Yes, we're taking a little hiatus because of various people. We have summer travel, and the American Astronomical Society meeting in Pasadena is the second week in June. So after that, after I get back from that, we'll have a live session. So thank you for your good questions as always, and Vicky for helping out behind the scenes, and Matthew for facilitating. So goodbye, everyone.